Ha, it's not on mute anymore. Okay, so as I was saying, you can see here what we did. We did it with our sigma notation, that Greek letter sigma, and we would go from this bottom little variable here. We'd start there at 1, substitute in for k, follow whatever formula there, and then keep going up by increments of 1 until we reach that top number up there. And that's basically what we did. And we did it for a few different examples, so you should definitely be familiar with these. And then just kind of went over the notation right there. If you didn't get it, you know, pause it if you're watching the video and get it. So let's go ahead and get into this. Here are some sigma notation examples here, and you can see different ones that you can do, and you can see what their summations are. So take a look through those, especially those ones with the -1 to the k. They alternate back and forth, negative, positive, negative, positive, negative, positive, like that. And then you could do -1 to the k plus 1, and they'd go positive, negative, positive, negative, positive, negative. And then a couple other ones down there where you just go through, you go over whatever the summation happens to be, and you do it. So let's take a look here at example 2, and we want to try to express the following sums in sigma notation. So I'm going to do this first one, and then I'm going to let you have a shot at the second one. So if we look at this, we see that we only have odd numbers. All right. And anytime, if you think about it, if you add a number to itself, it's always even, right? But then that means if you add one more to it, it's going to always be odd, right? So how do you add a number to itself? What do you do? If I just gave you a number, and no matter what number I gave you, you wanted to add it to itself, and you had one thing you could do, and you had to do the same exact thing every time. Yeah, multiply by 2, right? If I give you a 3 and you multiply by 2, you've doubled it. You've added it to itself. That's what multiplying by 2 says, right? Add it to itself. So if we think about this, we can get odd numbers by doing 2 times whatever number we have, and then just adding 1 to it. So 2k plus 1, right? Where k is an integer. Okay, where it's an integer. And so what we can do is try and take advantage of that. Notice we have to start at 1. Okay, so we're going to have some sort of summation here. We're thinking summation. We're going to have a 2k plus 1. We want to start at k equals something. Any guesses on what we should start at? 0, right. If we start at 0, then our first value is going to be 1. So we'll start at 0, and then where should we stop? Well, if we go to 9, we put 9 and we have 19. 4. 4, we do times 2, we get 8, plus 1 is that 9. And so we'll go all the way up to 4. So k equals 0 to 4. And if you look, that gives us 5 numbers, 0, 1, 2, 3, and 4. And you see in our little summation there, we have 5 numbers. So that works out very nicely. And if you were to do this, that's exactly what you get. There is another way you could have done this. Like I said last time, these are not unique necessarily. So how about this one? Tell me if you think this one is okay. Right, 2k gives us an even number. We're going 1 less than that, that's an odd number. So there's, we get our odd numbers. Start at 1, and you get 2 minus 1, that's 1, right? Go all the way up to 5, which gives you 2 times 5 is 10 minus 1, which is 9. And it would match all the other numbers in between. Okay? Any questions on that? Okay, go ahead and take a moment and try that next one real quick. I'll just give you a minute. Back here, I don't need to keep recording this. All right, let's take a look at this one here. So we have 2 plus 4 plus 6 plus 8 plus 10. So we're going by what here? 2s, and they're all what? Even numbers, and they're consecutive even numbers, just like the last one was consecutive odd numbers. So to do that, hopefully pretty simple. We just have to remove the plus or minus 1, right? 2k. And then we start at what? K equals 1 and go up to 5. Anybody think of any other versions? I mean, we can do this kind of like indefinitely here. We can do 2k plus 2, start at k equals 0 and go to 4. Right? So, and then you could keep doing that. You can change that little part and then change what you're actually summing over and just keep on doing that. What if you had this one? Let's do this one more real quick. What if you had 2 minus 4 plus 6 minus 8 plus 10? What one small change could I make here to get that one to work? Well, let's not put it. Let's just put C. So we can do this same sum, right? K equals 1 to 5 of 2k, but what change could I add on to there to make it alternate like that? Look back up here at that second one. You do what?
-1 raised to the k power.
Okay, so if we do -1 to the k, is that going to work? No, why not?
The first one is positive.
Yeah, and this -1 to the k would make the first one negative, right? So what do we do? Really close here.
-2k, 1 to the k.
No.
No.
then the one's just positive the whole time, right?
Yeah.
It'll be -1 to -k.
No. No. Well, I mean, I guess that would just flip-flop it. That's not too bad, actually, right? That would just flip up. Or you could just do this. Yeah, I think that would work though, right? Because you'd just be negating everything. So, but you could put that negative out in front. But yeah. Okay. All right. Let's continue on here. Any questions so far? No? Okay. Here are some algebraic rules for you for these finite series, and they actually should be pretty intuitive to you. If you're taking the summation of 2 terms that are being added together, you can do their summations individually over that same range. If you're doing the difference, I mean, difference is just the addition of a negative, right? So that rule should still hold. It's pretty much, to me, those first 2 rules are the same rule. And then constant multiple rule. If you're multiplying everything by a constant, you should be able to factor that constant out in front. So that should also make sense, right? If every term is multiplied by the same thing. And then, of course, if you're doing the summation of a constant value, it is simply, if you're starting at k equals 1, it is simply n times that constant value. So however many summations you're doing is what you're going to multiply by. And we saw that a couple pages back here, right? Where we did that letter D there. We summed from 1 to 3. So we did 3 of them, 1, 2, and 3. So 3 plus 3 plus 3, that's 3 times 3. Okay? So those are our little summation rules. So let's take a look down here and see if we can use some of these to show some of those rules. So if we look at this one, we can first off just use that second rule, which was subtraction, the difference rule right there. And we can make this into, from rule number 2, we can do sum 3k minus the sum, oops, that was not a good sigma, the sum of k squared like that. And we're going from k equals 1 to n, k equals 1 to n. And then after that, we can use the constant multiple rule and go ahead and make this one 3 times the summation k equals 1 to n of k, just like that. And then can we really do anything for that next one? I mean, it's k times k. We could split it into a sum of k times a, you know, but I guess we could do, but that's not really, you know, we're just going to leave this sum k equals 1 to n of k squared. Okay. So we did a couple of the rules there. We did rule 2 and rule 3. All right. So let's look at this next one together. What can I do here for this one? Yeah, that's going to be our multiple, what is that? Rule 3. This would be like having it this way, right? K equals 1 to n, whatever n happens to be, negative 1, a sub k, whatever a sub k is, whatever the term thing happens to be there. And then that's just going to be negative sum k equals 1 to n of whatever we're summing over there, or whatever. Okay? Any questions on that? Good. Try the next two. Y'all have these? No? It makes it kind of hard to show you the rules at the same time. Can y'all read that still? Zoom in maybe a little bit more, trying to get it all on there. There you go. How about that? Number C is 1 to 3. Number D is 1 to n. All right, so if we look at this first one, which rule can we use on this one?
The sum rule.
Yeah, the sum rule. And so this one, zoom in here a little, is just going to be the summation on k and then plus the summation on 4. And of course, it's still from 1 to 3, 1 to 3, k. You'll find that the more you do these summations, like the lazier people get about writing what the summation is over, up until you get to Einstein notation where you don't even bother writing the sum symbol anymore. That's in tensor math. And it was, I think it was the guy that used to copy his writing over more neatly noticed that every time he wrote a summation over something, the index repeated. And so the notation just became whenever there was an index that repeats, you sum over it. And then it was understood in his stuff, it was always summing over 4 things for the 4 dimensions. So anyway, people get tired of writing the summations is essentially it. And then what about this one? What rule could you use here?
Constant value rule.
What? Yeah, we have no k there, right? Yeah. So essentially what we have here is what? What's the ultimate? What is this ultimately equal to? 1, right? Because we're summing over 1 over n, and we're doing it n number of times. So n times 1 over n, and it's just 1. Okay. All right. Kind of a neat one there, isn't it? Yeah. All right. So let's keep going here. Keep this going. Let's look at example 4. All right. One such puzzle associated with sigma notation is finding a formula to evaluate the sum without writing out each term. Find a formula for the sum of the first n positive integers. By the way, an 8-year-old can do this. And I'm gonna leave that for y'all to try. You wanna try it now or do you wanna try it on your own? And then we'll go over it next time. I'll give you the weekend to try it. How about that? Try it and see what you can come up with, okay? See what you can come up with, and then we'll come back and look at that Monday. Don't let me forget though, okay? Because I will totally forget to go over it. Have it, if you get, just try it. Try it and see. Struggle with it if you need to. Okay, let's take a look at this. Limits of finite sums in section 5.1. We use rectangles to find approximate area under the curve. What happened as the number of rectangles increased and the subintervals became smaller? In other words, as we move from that left picture to the middle picture to the far right picture, what's happening there? Yeah, we're getting closer and closer to the actual area under it. So we're getting a closer approximation there. That one on the right is definitely a lot closer than the other two. Just visually, it's obvious that it is, right? Okay, so example 5, find the limiting value of the lower sum approximation to the area of the region R below the graph of y equals 1 minus x squared, all right, and above the interval 0 to 1 on the x-axis using equal width rectangles whose widths approach 0 and whose number approaches infinity. So we're going to add essentially an infinite number of tiny, tiny, really small, super skinny rectangles in there. Okay, just yay limits, right? So we have to look at our lower sum here, right? And I think this is the one we were doing before, isn't it? 1 minus x squared, right? And what did we end up coming up with what we thought it was close to? Anybody remember? Huh? Yeah, which was 2/3, right? So we thought this was going to 2/3, right? So that's what we're going to look at and see here. So first off, we need our interval width. And so we need delta x, our little interval width, right? That's this little width up here. Delta x, how much we change in x, how big of a step do we take in x? That's going to be b minus a over our number of, what do we call it? Number of rectangles that we want to do. I guess maybe draw a little rectangle symbol, number of rectangles that we want to do. All right, and we're summing this from A to B, right? Like this is A, this is B right there. Okay, so in this case, that's going to be 1 minus 0 over n, however many of these we pick, which is just 1 over n, number of intervals. And so the intervals that we would get would be the interval 0 to 1 over n, and then 1 over n to 2 over n, so on and so forth, all the way up to n minus 1 over n to n over n, which would take us to that 1, right? N over n is 1. So that would take us from 0 out to 1. See that? And it would be that however many, whatever n we picked, that's how many we picked. So if we pick n as 2, it goes from 0 to 1 over 2, which is 0 to a half, and then a half out to 2 over 2, which is a half out to 1, which would be that very first one we did there on the upper left. Okay, so we want to use the right endpoint when we do this, not the left one. We're looking at underneath it, the lower sum, right? Lower sum, so we're looking underneath there. In other words, when we have this picture and we're like this, our rectangles need to be underneath it, not above there where they're above it, not the upper one. So use the right endpoint. That's what we're looking for. Okay, and then we need to go ahead and look for this. So what we're going to say is our sum, we're just going to call it S sub n for however many n's we do, the sum for that certain number of n's, is going to equal our summation from k equals 1 up to n. We're doing f of k over n, right? We're not starting at the 0 one, we're starting at the first one. And then times our width delta x. This is then going to equal our sum on k equals 1 to n of 1 minus k over n squared. That's our 1 minus x squared. And then, right, because we're counting up first over n and then k over n and then 1 over, like that. And then, so we're just plugging in the k over n for x squared times our interval, which is our 1 over n. Okay? Make sense there? The k over n part coming from our 1 over n. Because our first value we'd want to plug in is not 0, but rather when k is 1 over n, and then 2 over n, and 3 over n. Those are the right values. And then that would give us that. After that, we can go through and start doing, we can start this here. We've got our sum, and then we've got 1 over n minus k squared over n squared. Okay. Or n cubed, sorry, because I brought that 1 over n inside there as well. So this is k equals 1 out to n. And then we can split this up using our rules, right? This can be our sum of 1 over n minus our sum of k squared over n cubed. And this is again from 1 to n, 1 to n. I'm getting a little lazy with my writing there, that's fine. Right? And then my 1 over n, we just did that one, didn't we? Our sum of 1 over n from 1 to n, what was it? Right, we just did that one on the previous page. What was it? 1, right? Because it's 1 over n times n, right? And so this one becomes 1. And so that gives us then this next one. And this next one we can actually make like this. So this is 1 minus 1 over n cubed. And I think here I have to use the one that, is that the one that we just skipped over? No, k squared's on there. So 1 over n, that's not the one I had y'all do. We were doing the sum on k, right? 1 over n cubed, sum k equals 1 to n of k squared. And if we look back one page, you can see right here, there it is. Sum on k of k squared from 1 to n right there. Is that n? And that's just on the previous page. So when you go try that one, you can see that here. You have a k squared and a k cubed. So this becomes 1 minus, and then we have our 1 over n cubed. And then we've got n times n plus 1 times 2n plus 1 over 6, just like that. And now we can actually distribute that 1 over n cubed in there. And you can see that we have this n here that's going to cancel. And so that'll become a 2. And what do we end up with? We end up with 1 minus 2n squared plus 3n plus 1. I also, multiplied those together over 6n squared. Okay? So whatever our subinterval n happens to be, if we pick 2, we can plug 2 into that and get our answer that we got yesterday or day before yesterday, whenever we did that, right? If we plug in 100, we'd get it. We can just plug in however many subintervals we want, okay? And we could plug in 1,000,000 and get a pretty accurate answer there because it's all just ins. You just plug in however many subintervals you want right there and you'd get your answer. But what are we trying to do here? How many subintervals are we trying to do? An infinite. So we need to take a limit here. So now we're going to let n go to infinity, okay? And then this should give us the actual area underneath it. So when we do that, we're going to be doing the limit as n goes to infinity of our s sub n, which is the limit as n goes to infinity of this 1 minus 2n squared plus 3n plus 1 over 6n squared. Now we just need to take the limit of both of those things, right? We can take the limit of each one individually. What I mean is we can do limit as n goes to infinity of 1 minus limit as n goes to infinity of that 2n squared plus 3n plus 1 over 6n squared. We agree, right? We can split them like that. Limit of a plus b is the limit of a plus the limit of b. Remember those rules? Okay. And so now we have that. So what's the limit of 1 as n goes to infinity? 1. So this will become just a 1. 1. And then what's the limit of 2n squared plus 3n plus 1 over 6n squared as n goes to infinity?
1/3.
2 over 6, which is 1/3, right? Because when you get to numbers that large, those squared values dominate, right? When you get out to infinity, the 3n and the plus 1, especially the plus 1, you're not going to notice them. They're gone. This is going to, you know, n squared blows up way faster than n, right? A billion squared is way bigger than a billion, right? 10 to the 18th is way bigger than 10 to the 9th. You wouldn't notice a 10 to the 9th compared to a 10 to the 18th. Okay, way bigger. So this just becomes, since those are the same, this is just 2 over 6, which is just 1 minus, what is that? 1/3, which is just, anybody? 2/3. Hey, how about that? What do you think you'd get if you did this as the upper sum? The same. In fact, I challenge you to try it. If you have a few minutes, try it. Try doing the same thing, but with the upper sum. You'll get the same answer. So we will count this as the area under the curve. Okay? Even if you wanted to try the middle one too. All right? That'll work. Come on, that's pretty cool, huh? That worked out for us. We got that 2/3 we wanted. Sometimes math does some neat stuff. Okay, any questions on that so far? Nothing on this? Okay. All right, let's take a look at this next one. It says calculate the area under the curve y equals 2x from 0 to 3. So let's take a look at this graph. Going from 0, 1, 2, 3 to 3. 1, 2, just like that. This is the graph y equals 2x. What kind of a graph is that? Straight line, right? So this has a straight line with a slope of 2. So we're just going to end up with this kind of a shape. What kind of a shape is that anyway? A right angle? Triangle. Okay, yeah. It's just a triangle, right? And so we know how to do the areas of triangles. What's the area of that triangle? Yeah, 1/2 base times height. What's the base? What's the height? 6. Good. So 1/2 of 3 times 6 is 9. So let's try this though, the old calculus way that we just did and see if we get that. So we expect and know pretty much know that's up at 6 that we should get 9. So 9, let's try it. So delta x, our integral is going to be 3 minus 0 over n, which is just 3 over n. Then we're going to do our sum from k equals 1 up to n, and we're doing f of 3k over n. So this is our right-hand side we're doing again. 3k over n times 3, or times just delta x first, delta x. And then this becomes our sum from k equals 1 up to n of, and we plug in 3k over 1, so it's 2x, so this is 2 times 3k over n times delta x, which is 3 over n. Just like that. This becomes then our sum from k equals 1 to n of, what is that, 18k over n squared. Okay, 18k over n squared, yep. And then after that, we can bring the 18 over n squared out front, 18 over n squared, and we have a summation from k equals 1 to n of k. And this is one that I believe that's the one I told you to go home and do, right? So I'll give it to you. Right here, it's 18 over n squared, and then that summation, and you'll now know what to look for as you try to do it. N times n plus 1 over 2. Which just simply gives us 18 n squared plus 18 n over 2n squared. And so now what do we do next? Yeah, take the limit, right? We want to take that limit as n goes to infinity. And so now we're going to say the limit as n goes to infinity of 18n squared plus 18n over 2n squared. What's that going to be? Yeah, 18 over 2, right? Those are the leading, the whatever it is of those polynomials is the same. Degree, thank you. I couldn't think of the word. Language is not my thing. All right, the degree of those is the same, and so we just take the ratio of those leading terms, right? Just like we did on that last one. So it's 18 over 2, which is just 9. Yay, what we expected, right? So see, even that worked out. That's how you do a really simple problem in a long, complicated way. Okay? Any questions on that? All right, let's go over here. I think this is our almost last thing here. So what we've got here is the Riemann sum. Also, I believe done by, I think maybe even before him, Bernhard. I don't know if he did it before or after. It happens a lot where you see things like, we'll talk about Taylor series and Maclaurin series, but Maclaurin did everything after Taylor and just did like a special case of Taylor series and really did nothing original, but yet some people still call it after him and stuff. So anyway, here we go. So if we look here and we have this function, you can see we can have negative areas and positive areas. So the part there that's in orange that's below the curve, below the axis, we would count that as a negative area. The part above there that's in pink, we would count that as a positive area. And so when we're looking at this and it's continuous, right? So continuous. We're going to have f, our function, is going to be bound from A to B. Okay. Supposed to be like a functioning f. we can have it being negative or positive, right? It doesn't have to all be just there. So it can be negative or positive. Okay. We can subdivide this, but not necessarily into equal widths. So subdivide, not necessarily into equal widths. Okay. Although it is easier to do it in equal widths. So if you have the choice, right? We're gonna choose n minus, that's an n, it's supposed to be an n minus 1 points n minus 1 points, and such that what do we have here? We have a is less than x1 is less than x2 less than so on and so forth, x to the n minus 1, and then b. So this would be like x0 and x to the n, where a and b is where we start. So those are all our subdivided points there. And then we're going to partition it. I'm going to run out of room here. So partition. P is equal to x naught, x1, x2, x n minus 1, xn, which gives us this x0 to x1, x1 to x2, and so on and so forth like that, right? All the way up to n. And this would be like 1 and 2 and 3 and so on and so forth like that. Those are our little segments in there, right? Well, you can see them right up there, C1, C2, all the way up to Cn. Okay. Our places where we're doing that. And then area of the kth rectangle. So area of kth rectangle is going to be f of ck times delta x sub k, whatever that width happens to be. And then the Riemann sum for f on interval a, b for partition P is this. Partition is the sum from k equals 1 to n of f of ck times delta x sub k. So just what we were doing before, right? It's just not necessarily divided up equally, doesn't have to be. And it's nicest, it is nicest when they're all divided up equally, when you make all the delta x's, the delta x sub k is the same. So keep that in mind. And then we can control this delta x by forcing it to be the largest interval. And so you control delta x sub k by forcing it to be the largest interval, which in this case, we we call largest interval called the norm of P, and it's written like a double absolute value sign there, like that. So the norm of P, like that. Okay, and so what that then gives us is, I know I'm really down here on the bottom, sorry. I started writing too big, is the limit as the norm of P goes to 0, SP is going to equal the limit n goes to infinity, SP. Okay. So we're going to take that limit that largest interval we have goes to 0. And that's the same thing as taking it as the number of intervals goes to infinity. Okay. Any questions? Okay. Take a look here. Find the norm of the partition P equals 0, 0.2, 0.6, 1, 1.5, and 2. So to do this, we want to figure out what the interval width of each one is, right? So if we look at this, we've got 0, 0.2, 0.6, 1's not as far, 1.5, and then also on out to 2. And so what's our actual delta x for each one? So here, our delta x, this would be delta x1. What's that going to equal? 0.2. And then here, delta x2, what's that going to equal? 0.4. Delta x3, 0.4. Delta x5, 0.5. And delta x6 here is what? And so what's the largest of our intervals? There we go. Okay. All right. So we didn't get here. I'm going to go. So that's it for 5.2. Let me go ahead and stop.